Is it 2018 already? Postdoc, the New Orleans ACS meeting is coming up. I need data. Again. Yeah, I got a little bit of data to present, but I really need some new equipment. New equipment. Well, time to make it rain.
Damn. Yeah. Yeah. Yeah.
Woo! Nice. This is awesome. You have no excuses now.
Yeah. Yeah.
Hello, everybody. Hello. How are you doing? My name is Alex. I'm an electrochemist at Pine Research Instrumentation, and welcome to another episode of Ask Us Anything about Electrochemistry. My colleague Neil is on vacation right now. He'll probably be on vacation for maybe another week or so, and also next week I won't be in because of work and other things. But we get a lot of questions from people on the internet, through phone calls, emails, YouTube, webinar, all about electrochemistry. And sometimes those platforms are not the best for answering questions. It's hard to, sometimes writing a comment for a YouTube video is not necessarily the best way to answer that question. Sometimes a bigger description is required. So we have this live stream to hopefully answer questions that you may have about electrochemistry. We try to run these live streams for about 2 hours, where you can type in your questions on either YouTube or on Twitter. Hopefully in the future we also broadcast on other platforms as well, as long as they have a video component. And we have found that this will be episode, I believe, 59, in our almost over a year of doing these live streams. We have found that we're pretty good at answering general questions about electrochemistry. Some of them we can't answer if they're very, very specific questions, like what's the activation energy of a very specific molecule. We're not going to know the answer to that. Similarly, if you have a very general question, like just what is cyclic voltammetry, if you're looking for a very detailed answer, we can give you a general one, but maybe not as detailed as you want. So questions that are kind of in the middle, clarification about concepts in electrochemistry that you have, are things that we're pretty good at doing. If you are watching this live stream after the live stream is done, we should have some timestamps in the description below. So if you missed the live stream, you can always just look at a question that was interesting to you at a later time. Also, apologies in advance for mispronouncing anybody's name. It's just a YouTube handle or a Twitter handle, so you could put anything there, and I may or may not be able to pronounce it. With that said, let's get started. So I actually have we had a question just a little bit earlier, so I didn't get it into my feed, but if you can see this, let's just remove that. Here we go. So this is a question from Alex and from Barry. So we'll first answer Alex's question. Alex says, I'm using a mixed solution of 2 different metal ions to electrode deposit 2 metals from CV scan, from plus to minus. I got 2 reduction peaks at 0.4 and negative 0.7. Which potential to apply to deposit both together? And then he also says, how to know how much metal is deposited if I use the potentiostat method based on its reduction peak in CV to electrodeposit the metal from its ion solution. Please give some detailed calculations. So let's talk about this. I'm going to make this a little bit bigger. So what Alex is describing, to my knowledge, is you're getting a voltammogram that looks maybe a little bit like this. I'm just gonna going to draw some stuff here. So Alex, please correct me if I'm wrong in how I'm describing this. Let's make this a little bit thicker. All right, so this is your voltage. You got a current. You are getting reduction peaks. So I'm going to use the IU-PAC convention for plotting U-PAC. This may look a little bit different, but the information is still the same. You're starting at a positive potential, and you're sweeping negatively. And as you sweep negatively, you get one peak at about 0.4 volts. And then maybe that goes down. And then you get another peak here at, say, what was that, negative? Let me just go back. So that was negative 0.7. So it's not to scale right now. So negative 0.7. So this is not to scale. But so you do this voltammogram. I don't know if you sweep the other direction, but maybe you sweep the other direction and it's a flat line. So these peaks here are associated with the reduction of two metals. So you have maybe like metal 1. So actually, let me just draw that a little bit clearer. So let's just call this, we're going to call this A plus an electron goes to B, and B is adsorbed. And then we also have a second completely different ion, which is C plus an electron goes to D. That's also adsorbed. Okay, sorry I don't draw very well. And leave a comment if this is good, or if I'm on the right track. I'm trying to describe this as clearly as I can. So this is what I assume is happening. You have these two metal ions in solution. So maybe they're +1 or +2 or something, and you're reducing them on the surface. And your question very specifically is which potential to apply to deposit both together. So in this, I'm assuming these happen at these are two different redox potentials. And if you were to look at, say, a table, right? So if you're depositing nickel or if you're depositing copper, the reduction potential for both of those are different, and it should result in two peaks. This is also a very interesting case because you are kind of have both of these in solution at the same time. It makes it sound like D is basically adsorbing on the surface of B. So if you just had C in solution, this potential may shift or this reaction may not happen because you're not just on an electrode surface, you're on this adsorbed, reduced metal B on the surface. And actually, to be a little bit clearer, if we want to be a little bit more technical, I should realistically draw it this way. What you actually have is you would have something like A plus going to A, solid. This is a solid thing, and this is an aqueous thing. So there would be a plus here. There's a plus here, and then you have C. That's also a solid that's adsorbed onto the surface. So that's what you actually have. Now, the question regarding calculations, how do you know how much of this is actually on the surface? How much C and how much A is on the surface? So in cyclic voltammetry, there are a couple things to keep in mind with regards to how much. Normally, so there are a couple assumptions that you need to make when doing the calculation. One assumption, and I can just can type this out. So I'm just going to assume, just going to type this out. Assumption when calculating amount of A and C. So the assumption is the following: is that all of the current in the peak, more specifically, all of A plus, goes to A as a solid, and all of C plus, let's see, goes to C as a solid. And the reason why I say this is because it's oftentimes the case that the current response you get is maybe diffusion limited, right? So you have your molecule diffusing towards the surface, and then they diffuse off the surface. You're assuming that none of the, whenever you have the electron transfer, the solid is not coming off of the surface once it's reduced onto it. Okay, so that's one thing. There is a technique known as anodic stripping voltammetry. And I will talk about that later. That goes into a little bit more detail as how you can quantify this from just cyclic voltammetry. But once you make this assumption that that all of your A plus in the reduction is going to a solid that's plated on the surface, what you need to then do is let's do a quick thing. I am just going to review. I'm going to delete some of this here just to make some space. So I'm going to delete this. I'm going to zoom in. Actually kind of zoom in on one peak. So I'm just going to draw this. And let's just look at one peak here. So let's just look at one peak. There is some current associated with electrical double layer charging. So there is a current here that's associated with the electrical double layer, sometimes referred to as CDL. It's a background current. So that background current cannot be used in your calculation. You have to, quote, remove it from your calculation. You have to calculate the area of this. And all of this area is associated with the amount of, in this case, A going to A adsorbed, whatever you have plated. All right. So it should be relatively sharp. If you have a diffusion-controlled process, right, this is where the assumption comes into play, then this should stop. Then it should stop. Like once you've plated a layer of A onto as A solid, this should basically stop, and maybe you just have double layer charging, and the double layer will charge. So that is what you need to do. And one thing that can be helpful, let me just make sure that if there's any other comments. Nothing from Alex. So if I just share, if you are using, say, our Aftermath software, just make sure it's sharing. Okay, good. So I have a voltammogram of, let's see, that's just concentration before Tylenol. So this is a cyclic voltammogram of Tylenol. Usually in these voltammograms, you're not going to want to look at the current versus the voltage. You need to look at the current versus the time. And we have some tools in Aftermath. I can select, I can use an area tool. And I can use the tool to generally get some kind of level or estimation of how much charge is being passed. So this is what I want to do. I want to get my voltammogram. I have a peak, right? So maybe this is the peak. This is an oxidation reaction. You're going to be looking at reduction reaction, so you'll actually be looking at this, but the way to do it is still the same. And in this case, I really don't have very much current associated with double layer charging. It might be negligible for your calculations, but this is just how to do it correctly. But you're gonna have to make an assumption about, well, how much double layer am I removing? So maybe this line that I'm basing this on. So I'm gonna zoom in. Well, how much of the double layer am I looking for? Do I want to move? So I may actually say, maybe it's this much, or maybe it's this, and I only want to calculate from this area. And so once I know, like, oh, this is the area. Let me just zoom back out again. This is the area that I want. this area in coulombs, in this case 72.2 microcoulombs, is associated with the reduction of A to A solid. That's what my reduction is. And I would then use Faraday's law. So I will, I wonder if I actually have, it's not necessarily Faraday's law. So Faraday's constant, is, I never remember it, but it's 69,485 coulombs per mole. And so you would take it's coulombs per mole. You would take the number of coulombs that you've calculated in Aftermath, and then you would divide it by Faraday's law, and that would give you the number of moles of your species. And once you know the number of moles, and you know time x, you now have the mass basically of how much metal you deposited. So one last thing I would just mention about this is, because cyclic voltammetry, it gives you a current response, it can be very useful. There's another technique called anodic stripping, and I would also recommend maybe using anodic stripping. Anodic stripping is when, after you've plated something, you literally strip it off. So in almost a separate solution with whatever your film is, you would then put it into solution and then just, basically do a cyclic voltammogram going the other way, and you would get a very like kind of sharp peak, or just a big area peak, and all the current that's associated with that oxidation would be associated with the stripping off of your metal. And that's I would compare the current associated with plating and stripping off when quantifying how much you've actually deposited for both metals. So I hope that is helpful, Alex. Now moving on to Barry's question. Let me pull up Barry's question just quickly. So Barry had a question. Make sure it's being shown. Yep. So Barry had a question. When using screen printed electrodes with a silver chloride reference on them, why do I need a second silver wire in solution? Or why do I need? So you don't have to have a second silver wire in solution. You can use the onboard reference electrode. And so let me actually just pull up Pine Research website so that people know what I'm talking about. So give me 1 minute to pull up these electrodes. And if I share my screen, nope, it's Chrome tab. Okay. So if I share my screen, you should hopefully see this. Yeah, so these are screen printed electrodes. These are the ones offered by Pine. The reference electrode is this, the reference electrode is this little dot. It's this little like silver chloride dot that's on the screen printed electrode. There's another one here. The difference between these is this is 2 millimeters and this is 5 by 4 millimeters. But you don't necessarily have to use a separate reference electrode. The reason why we might recommend using a separate reference electrode is that this silver chloride dot, its potential will shift and change as a function of the analyte or the electrolyte concentration. So it can change during solution. It can change, and it's not very well characterized, sort of say. So we do, and if you're using a non-aqueous system, which if you're using non-aqueous, you might not even want to use these because it'll dissolve. The blue polymer binder actually dissolves the insulator. But yeah, if you use a silver wire, like a quasi-reference, like a pseudo-reference electrode, or quasi-reference electrode, sorry, and you have that exposed, you have a frit, you put some kind of analyte in it, something to govern the redox potential, then that also works. So I don't actually think you have to use, I don't think you necessarily have to use a silver wire, but some systems, if you still want to use the screen printed electrode, but the reference is not behaving well, but the working and counter are fine, you do have the option of using an off-board reference electrode. So you can use a silver wire in that case. So Barry, I hope that answers or addresses your question. Okay, moving on. Thank you all for joining. Let's see. We have a question from Fred. Everyone's doing electrodeposition. I'm doing electrodeposition using chronopotentiometry. Is the set current negative 0.7 milliamps very small? Distributed evenly on the submerged substrate. So the net current will be divided by the surface area. Yes. So if you have a big plate, if you're looking at the current density, then yes, the negative 0.7 milliamps will be distributed across the entire area of the working electrode. Now, let's see. The question is, will it be distributed evenly? I think that's going to depend on your working electrode and and just kind of how the surface morphology of the working electrode is. If it's very flat, if you have a uniform solution, if you have good stirring, if you have good mass transport, if you are using mass transport, or if you're controlling mass transport for chronopotentiometry, then yes, it will. Let's see. You have kind of a separate thing. So, or the whole submerged substrate gets the same current. Okay, I see. So ideally, the whole submerged, I would say the current density. So when you set your potentiostat in a galvanostatic mode, and you say, okay, apply minus 0.7 milliamps, it just makes it so that current is going to flow between the counter and working electrode such that 0.7 milliamps of current is measured at the working electrode surface. How that current is distributed may very well be based on the morphology. It's certainly based on what is submerged into solution. So if you have a plate and it's maybe you have an alligator clip on it and you submerge it in, well, there's some parts that might not be in solution. Well, they're not going to feel any of the current. But the current in these experiments, one thing that's always interesting is, the potential is allowed to drift to drive whatever current you told it to. So it can be very helpful if you start to see the potential change wildly, or it's steady for a long time and then it starts to change. It means you've usually depleted whatever your substance is, because then the potentiostat's looking for, okay, well, what's the potential to continue to drive that much current? I need to now do the next best thing, or which may be eating up electrolyte. So, but will you have even coating on the entire surface? I think you'd need to do a kind of microscopy technique to image the surface, maybe use AFM or something like that to see whether or not you indeed did uniformly coat. One thing, I don't know if there's a good way to do this. There are these like 4-point probe techniques, but that's different than like electrode depositing. So Fred, I hope that was helpful. Let me know if you have further questions or if you want more clarification or if you have more information. But I hope that was in some ways a satisfying answer, or you learned a little bit more. All right. Moving on, we have a question from Bill. Bill is saying, or is asking, the deposition of a metal during the cathodic scan does not always show reduction peak. Sometimes it shows continuous increasing current. Can we explain why this can happen? Yes, I think we can. Possibly. Why it doesn't result in a peak. So the reason why we get a peak in a cyclic voltammetry experiment. When we think about a peak, we need to think about the current is changing as a function of potential, but it's really changing as a function of time. So the current will increase. It reaches a maximum rate of deposition in a deposition experiment, and then it trails down. It no longer tends to the rate at with which it's depositing slows down, and this is usually almost always mass transport limited. So it's almost always mass transport limited, and if you see a continuous increasing current, that means that it's most likely still plating. And you probably, at that point, it depends, I think, a lot on the concentration of the species that you have in solution. So if you're depositing something and it's continuing to deposit, and you literally, let's say if it was nickel, for example, you're reducing nickel on the surface, you put some nickel on, and then, well, there's now more nickel that's like on the surface. Like, so you're putting more nickel on and more nickel on, and there's new nickel, and so that nickel keeps going on. And just to kind of just draw something very very quickly, just to kind of, let's see. So let's go here. Let's erase this guy here. So, and then I can delete that. So if you're getting something where, and this is cathodic, so we're seeing a decrease in the current over time, right? So maybe it's like that. That's your deposition. That's your A plus an electron. Maybe it's in equilibrium. Maybe, well, actually, in this case, it's just going one direction. So so it's just going one way, and it's forming A, solid on the surface. If you keep having layers and layers on top of it, you never get this peak, right? That's probably because it depends on the voltage range. Is going to be part of it. There actually may be several things that might be happening in this situation, but you have some kind of bare surface, and then you have like a row of A's generating, and then you continue to have A's, just plating on the surface. And so normally, in normal electrochemistry, when you have something that's like that's like a peak, it shows that the rate at with which these A's are going on the surface is decreasing, and this peak always arises due to a mass transport limitation. But because the A, there is no mass transport limitation, you generate some new A, that A disappears, and there's plenty of A plus in solution, just kind of there, and it just very easily moves to the surface. You are also making the reduction potential more and more negative. So kinetically, you're increasing the rate. You're providing more driving force to get these A's to reduce to A solid. When you have a traditional peak, once you have converted something like A, when you have A plus going to A, there's A that just kind of hangs out in solution. And you're waiting for diffusion of an A plus to kind of make its way to the surface. That's the thing that slowly, that's the thing that makes it so that this doesn't go up forever, but actually drops, because you're waiting. It takes longer for an A plus that's further out from the diffusion layer to make it towards the electrode surface. So that is why, that may be one reason why you're not observing a peak. Additionally, you may also be getting to potentials where other processes are happening. So there is usually some kind of good area where you're doing the reduction reaction, but there can also be there may be other reactions occurring. Like this A may be catalytic for another reaction. Remember, the current that you measure is the net current. It's all the things happening. So, A solid plus another electron plus water might be generating O2 or something, or maybe generating hydrogen gas, right? You might be reducing the protons from your water to hydrogen gas. There may be more reactions that are occurring, if you're doing this in water, which I assume you are. So that hopefully explains or provides some wisdom as to why you might not observe a peak, but a continuous increase in the current. So that you're constantly reducing something at the same rate. And the increase in the rate, the current, is because you're driving the potential more and more and more negative. So hopefully that helps. Chris makes a comment. Chris, always good to see you. Surface structure can cause odd responses. You have different potentials present along different axes of the lattice. Yes, yeah. So on a microscopic level, the actual potential that is felt can be different on the microscopic level. So that's it's a very, very, very good point. I don't know if I don't have any like tools necessarily to help you understand, to help people do that. I think you would need to use like a scanning electrochemical microscope to really look at it. Let's see. I'm just gonna check on things. Let's see. Okay. All right. Just checking comments, checking Twitter to see if Twitter folks have any questions too. Okay. All right. So we're good. All right. Moving on. Narvekar is asking how to calibrate a non-aqueous electrode. It's a good question. Good question. All right. So let's see. So for non-aqueous electrochemistry, ferrocene is considered to be a well enough studied molecule that ferrocene, the oxidation reduction of ferrocene to ferrocenium, is well studied and well characterized. So let me again erase all of this stuff, and I'm just going to write it. Just type it out. So ferrocene. So ferrocene can be an internal standard, and it can be used to for doing non-aqueous electrochemistry. So when you, and there are many ways of doing this, really. When you're doing non-aqueous electrochemistry, and you have, say, a silver wire. So some people just use a silver wire. Some people have a silver wire in a fritted tube with the analyte. So this is also an AG wire. And then they would fill it with their electrolyte. So just put some dots here. So that's one type of reference electrode, but the potential is unknown. You may even add something like AgNO3, nitrates, just to have silver. You may have a silver, silver plus an electron to get you silver might be the redox couple that will govern the potential of your reference electrode if you just have a silver wire in a non-aqueous system. But what you can do is you can do some electrochemistry, and maybe you get some peaks and some stuff like this. But what you can do is you can add ferrocene to the system, and as long as ferrocene is not doing any chemistry, it's not participating in the system, you can get a nice, well-characterized, this goes the same thing. You can get a nice, well-characterized voltammogram of ferrocene, which would be this guy. And then you would make ferrocene your zero. So you can shift the potential. When you have all your data, and this may be zero with your silver wire, but this is zero versus ferrocene, sometimes referred to as FC plus. So you just add a little bit of this to the end of your experiment. You do all your experiments, you do all your CVs, and then you do you add ferrocene, and you'll observe, like, okay, did your experiment shift during the course of the experiment? Maybe. If so, add ferrocene, and we know what the redox potential of ferrocene is. It's at least well studied. And this is a good way of saying, okay, it's common to report what your potential or what your electrochemistry is with respect to ferrocene, the FC plus redox pair. And so ferrocene can be used in acetonitrile, THF, DMSO, dimethylene chloride. You need a good electrolyte, but referencing to ferrocene can be very helpful. And there's a way of solving that problem. Okay, so let's see. All right, going down the list. So we now have, stop sharing my screen. Weinero. Again, I apologize for pronouncing or mispronouncing people's names. I have a question concerning the EIS. I'm researching a corrosion system. In my EIS, I see the expected semicircle. Okay, that's good. Also, I'm going to give you a heads up. Neil is the EIS expert. I will try my best to answer as much as I can, but he's the one who has a little bit more hands-on experience with it. So I'll try to help you as much as I can. The problem I currently have is that sometimes the last few points, 3 to 10 data points in the low frequency data, is shifted upwards and to the right. The Kramer's curve transformation says these data points are bad. I understand. However, I do not understand where the shift is coming from. It's almost like it almost looks like artifacts and not really like it's caused by system instability. Any thoughts on this? The frequency range is, and then he mentions that the frequency range is between 100 kilohertz to 0.01 hertz, so 10 millihertz. Okay, this is a very good question. So the last 3 points are shifted upwards and to the right. KK transformation. So these data points are bad. I do not understand where the shift is coming from. So the way you describe it in a way, and I'm not the best at corrosion. I'm trying to think. So usually, one thing I think about is like, all right, you have some like kind of stability issue. Something is causing instability, especially in the low frequency range. So I don't think it's uncommon. Z real, and then negative Z imaginary. And then I'm just assuming you got something like this, semicircle, and then maybe you have something here, and then your last few data points are just kind of like shifted up and to the right. Right there. It's like it just like goes up and then it's off. And so that's what's causing you some problems or something. That's kind of my initial guess as to what you're looking at. And yeah, what could be causing it? I don't think it's uncommon that at the low frequency range you're seeing disparities, because it can be drift. I think we'd also need to know a lot more. We need to know a bit more about your specific system, because I suspect sometimes I would ask, is the reference electrode shifting at all? If you're doing these experiments and they're corrosion experiments, I do wonder whether or not the reference electrode potential has shifted, especially at these very slow frequencies. But maybe something else is also occurring that could be shifting the system. Let's see. Oh, he's saying, okay. Correct. Basically, just offset from the rest of the other data. Okay. So it's just offset. Huh. Okay. So let me think about this to see if there's I have any insight. So it is as if it should be like just lower and to the left, but instead it's just moved up and to the right, but then it just continues as normal. Let's see. It's It's a calomel reference inside a Haber-Lugin capillary. That's fine. Calomel is a very stable reference electrode. Yeah. Let's see. What could be causing a shift in just low frequency points? So one thing that I always think about, well, and I guess my other question is this consistent? Like, have you done this experiment numerous times and you always see the last 3 to 10 data points in the Nyquist plot shift like up and out, and then it kind of looks like okay or normal? So that's another, I guess, kind of question I have. Yeah. And it's a corrosion experiment. Oh, so one thing I would also ask or think about, because you mentioned that this is corrosion, right? So is there any physical, let's see. So, he's saying not always, but in 70% of cases. Okay, all right. So it doesn't always happen. So one idea I just thought about is if you're doing corrosion, there's a real chance that if you're doing corrosion on these very slow, much slower frequencies, there is a chance that, I'm just taking a stab at it or a guess at it, but maybe some of the corrosion is occurring and it's flaking off the electrode. And maybe it's just one little flake, and at the 10 millihertz frequency, it's like, well, that's enough time where it's like, yeah, you're able to, it flakes off a little bit, and then it just shifts everything. But because the current is different, in all of these measurements, remember the impedance is still it's still voltage divided by current. So I can also think of it this way: if I'm getting a shift to the upper right, and I'm just thinking this through, I don't know if this is true or not. I'm thinking if my impedance all of a sudden jumped up higher, because if it's going up and right, I think of that as like capacitive in a way. It's like for anything going up, there's a capacitive element that is either developing, you have a higher impedance there. And then if you have a, let's see, so it's when it goes up, and then if it goes right, you have more, quote, of the real component of the impedance increasing. Are you creating something? Is something new being created? So yeah, and Chris has a comment: is there a passivation layer forming with a long time constant? That could absolutely be the case. Neil has mentioned in the past that sometimes these passivation layers will form, and it gives incorrect results when you're talking about testing like a corrosion inhibitor. So you add the corrosion inhibitor, but you get like a false positive on how well the corrosion inhibitor is working, because the nature of corrosion also creates a passivation layer on top of it. Let's see. So the system contains a small amount of chromium, so some passivation is expected. Yeah. Yeah. I am wondering, so a couple things. Again, I'm not the best EIS expert. I do wonder whether or not, I think there's a minimum of about like 6 to 7 points per decade for EIS. I don't know if maybe you're taking more EIS measurements than you need to, and you can try to get away with maybe taking a few, like maybe fewer data points to see whether or not, like, okay, this passivation layer does not form. I should have asked whether or not there's mass transport in this thing. Like, are you rotating like a rotating cylinder electrode, or is it just completely stationary, just in solution kind of thing? 10 ppd are used. I don't know what ppd is. And then if you shifted the bias voltage to help characterize that. That's another, that's actually another great point from Chris. You can try doing EIS at different potentials. So even if I mean, corrosion is supposed to occur at the OCP, right? So maybe, I mean, that might be tough because corrosion, you'll definitely be inducing some corrosion if you're doing EIS not at the OCP value. I have to think about that. I'm not so sure I know what's causing the sudden jump. I will say, and I don't know enough about. Let's see. So yes, the system. Oops. Hold on. He's saying yes, the system was statically polarized anomically for 60 seconds, about 24 hours before the shift occurs. Okay. All right. Interesting. Yeah, that can. If it's polarized anomically, then. Oh, okay. So you're just trying to. Okay. So you are in a way forming a. 24 hours before the shift occurs. Like, I don't know. If it's 24 hours, like, I don't know if that's what's causing it. Sometimes I wonder about whether or not there's a very specific frequency where this is happening at. So if it's happening at like, okay, this frequency exactly, and then a shift, and then it looks normal. I do wonder whether or not there's some kind of electronic thing that might be happening. And if you were to pick a slightly different frequency, not frequency range, but if you change the number of points per decade and it recalculated where, the frequencies would be taken, I wonder whether or not that would affect it as well. The shift does not appear in the EIS data. I think you're talking about the post. Interesting. Yeah. So, I'm not 100% sure. I know like exactly where it's coming from. I want to say maybe check the reference electrode, but that's not always the best thing. I don't think I have not checked the frequency range yet, so we'll do. That's a good idea. Okay. All right, that's one suggestion. Just an idea. Hopefully that's helpful. In about 2 weeks or so, I think Neil will be back, and then we can you can ask Neil this question when he's back from his vacation. But he will be out for a while. I don't know if he's going to be back. I don't think he's going to be back next week though. So yeah, I'm sorry. Can't give you a absolutely solid answer, but yeah. Okay. All right. So just going down the list, Enrico is asking, what would be a good recommendation for a book to begin with electrochemistry? That's a good question. We're commonly asked what book is a good electrochemistry book to use and learn, a beginner book. One book that I always have, but it's absolutely not a beginner book, but it's a book that every kind of pure electrochemist has is Barton Faulkner. It's third edition of Electrochemical Methods, Fundamentals, and Applications. If you're doing electrochemistry in the long term, this is a book that it's very good to have. It has all the derivations and explanations for things. It's a very thorough book. Not a perfect book, but a thorough book. But many people find it to be very dense and difficult to read. There's another book. Let me see if I can find it. Electrochemical. It's called Electrochemical Engineering. Here we go. So there is this other book that I'm just trying to get the front cover of it. Okay, let me share. Okay, so there's this book here called Electrochemical Engineering by Thomas Fuller and John Harb. Again, I'm not very good with names. I have found I'm not an engineer actually, but I have found that this book, it's relatively it's a smaller book. It's actually it's a taller book, but it's less pages, and it goes over. It doesn't go over like all the detailed derivations of every single thing in electrochemistry, but it gives like it has very good pictures, good descriptions. I actually think it's a very good book for learning electrochemistry. It's not ultra intimidating, as Barton Faulkner can be, as it has a lot of complex math. Additionally, the book has a lot of examples of things. It actually like has numbers and how you can do some calculations. So I have found this to be a good book, possibly for beginning to learn electrochemistry. Yeah, unfortunately, there are not too many, not too many good books for learning electrochemistry for the first time. Okay, all right, moving on. Nathan is asking, hi, I am a beginner learning about cyclic voltammetry. Could you please explain the relationship between a cyclic voltammetry graph, duck shape, with the standard reduction potentials? Sure. So one way to do this may actually be through software. So I'm going to share, this is our Aftermath software. I'm going to hide your thing. I'm just going to show you the relationship. So what I'm going to do, I'm actually going to simulate this. We have this simulation software, which actually I think is very helpful when it comes to learning electrochemistry. So make sure everybody can see. I'm going to make this full screen. It's called Aftermath Live. And I'm going to create a cyclic voltammogram. This is going to be a reduction reaction. And this is going to be my cyclic voltammogram. I'm just going to sweep from 1 volt to minus 1 volt and back. And when I simulate it, I get something that looks like this. So here is the voltammogram, the classic duck shape that you are looking for. And the reduction potential for this particular reaction, which is A plus an electron going to B, is at 0 volts. But I can shift this around. I can make this like minus 200 or minus 200 millivolts. And you'll notice if I do that, this whole peak, both of these peaks are going to shift to the left. So if I simulate it, it shifts over to the left. And if the reduction potential is positive, and I hit simulate, it'll shift over to the right. So the potential, the E naught that you see in textbooks related to at what potential does lithium or copper undergo an electron transfer or oxidize or something like that. That potential is this E naught that you can measure in the lab with cyclic voltammetry, and it represents, in this case, for a very fast electron transfer reaction, it represents the halfway point between this peak and this peak. And more specifically, it represents the point where the concentration profile, so during our voltammogram, you have two things. You have you have species A and species B. But the point where their potentials actually intersect, so I'm going to try to very carefully get to basically the midpoint. Right when it's at this midpoint here, when the concentrations are equal, and I don't think I can iterate just enough, but pretend that these two are exactly the same. When the concentration of A and B are 50-50, that actually aligns with 0 here. It's a little bit hard to see because I've gone just past it, but when this is 0, when the concentration is 50-50, it has reached the peak potential. And so it's not the reduction peak or the oxidation peak potential. It's kind of halfway between, or sometimes 70% either way, depending if your electron transfer kinetics are sufficiently fast. So I hope that, Nathan, this kind of answers your question. But yes, that's the relationship in a cyclic voltammetry duct with the standard redox potentials. And again, this is Aftermath Live. It's I actually have a solid software version of it, but it's a simulation software, so I can simulate cyclic voltammograms, estimating things like the potential, the rate constant, alpha. I can also change things like the solution resistance, the diffusion coefficient, the concentration of species. So it's actually very helpful for learning electrochemistry. So for those of you who are interested in learning electrochemistry, I'd recommend going to aftermathlive.com, maybe just getting the student edition or the basic edition for like a month and just playing around with it and seeing how the voltammogram changes as you change these parameters. I've actually learned a lot of electrochemistry from doing that. All right. Moving on. We have a question from Fred. Fred also asked a question earlier. This is his second question. Thank you very much. Very informative. I think it'd be better to use chronoamperometry with sufficient potential instead to get better coding. So you need to know the needed current density and the submerged surface area to get a homogeneous and reproducible coding correct. Right. So you need to know the current density, submerged surface to get a homogeneous. So I think that there's actually two things. I think there's a lot that's involved in codings to it's a little bit of trial and error, and I hate using that because it just seems like I just don't know what the answer is. But the factors that really go into creating a homogeneous reproducible coding, it has to do with surface conditions. It does have to do with the potential applied. It also has to do with things like mass transport. There is additionally things like the position of the counter electrode. So if you're plating something else either has to be leaching off or coming off. You have a counter electrode doing things. The current flows from the counter electrode to the working electrode. While it usually doesn't affect most experiments, if you're doing large area coatings, the position and geometry of the counter electrode, kind of the field lines between the counter and working electrode, how the current physically passes between those two, can affect how it's coded. So I'd even look at your counter electrode as well to help with understanding reproducible codings. To a degree, like chronoamperometry, like you can apply a nice high potential and then get the reaction to occur. The way I think of it is chronoamperometry, you control the potential, you're controlling the thermodynamics of like only these reactions that are thermodynamically strong enough or at the right thermodynamic potential are going to occur. So I'm only going to be doing this coding. But you will almost quickly find that the rate, but the rate can change, the current can change, so the rate of the deposition can also change. And maybe the rate of the deposition is very important to getting a homogeneous coding. If you do chronoamperometry in a typical configuration, it starts high and then it goes very low. So it might not be something that you want. It's unfortunately the reality that you have to play around with some of the parameters and then test what you're looking for. Like, how are you measuring uniformity? You may have to play with some of the parameters. I mean, some people have the solution stirring. So if the solution is stirring while you're plating, you might need to change the speed at with which it's coding, or the speed at with which it's rotating, a stir bar, or something along those lines. So all of those things will play a role. So the surface, the counter electrode, the concentration of your species, the electrolyte, the solution resistance. Sometimes if you're applying a lot of current, you can actually get heating in your solution. I mean, that can also happen. And that also changes things. So it's definitely an engineering task to try and optimize the parameters to have uniform metal deposition. But a lot of people do it, and it just depends on how detailed you need it to be. All right, so I'm going to scroll down a little bit more. Let's see what other questions we have. It looks like Noreen. Noreen asks, in overall water splitting, electrochemical active surface area, ECSA, is determined separately for HER and OER for the same electrode. Is it possible for an electrode to have two active surface areas? Oh, this is a very good question. Chris has also started talking, answering this. So I'm going to see what Chris has to say. Let's see. One case I can't think of possible would be nanostructured porous surfaces. Some semiconductor systems can show a similar effect. Yeah, I could. Semiconductors are very complicated. I'm still wrapping my head around the science behind them. But in general, we have it. I think you might be onto a very interesting, just general research science topic that people don't really know about or appreciate, which is the idea like maybe there are two active surface areas. So you can, in principle, the answer is no. There are not two separate electrochemically active surface areas. Well, I should say that differently. There's only one area for the electrode, but you might have more than one active area for a particular analyte that's bound to a certain species. So for example, let's say you have polycrystalline platinum, for example. Well, maybe there's a special reaction that only occurs on platinum 111. And then there's another reaction that occurs on platinum 100. Well, the amount of exposed platinum 111 and the amount of exposed platinum 100 may be different, and hence the measured electrochemically active surface area for that specific thing may be different. That may be a possibility. However, it is our general understanding that you only have one active surface area, and that's the surface area where chemical reactions can occur. But you know, it may be the case. You may that's a PhD. That's that's not a PhD project. That's like a research professor's career, is like figuring out if that's true. Like actually looking at multiple different systems to see if the electrochemically active surface area can be different. There are ways of calculating electrochemically active surface area. I wouldn't be surprised if you used two different methods and got two different numbers. But those two different numbers should be very close to each other. You're just looking at subtle inaccuracies regarding how each technique works. But ideally they have the same electrochemically active surface area. And sometimes, you know, if you're using a molecule to probe it, that the area, like a redox reaction, you know, so like the for example, let me show you useful equations. So in cyclic voltammetry, we have this is the Randall-Sevcik equation. And it just describes that the peak current's equal to a whole lot of different stuff. Let's just say it's at room temperature. You have some constants, number of electrons, concentration, the scan rate, the diffusion coefficient. but there is an area. There's an A here, right? And that A is supposed to be the electrochemically active surface area. But I bet that if you had different molecules, and you took into account their diffusion coefficients and you measured the concentration very well and all that kind of stuff, you might get different areas because a molecule may be a little bit bigger or a little bit smaller. But that should ideally come out in the diffusion coefficient. But maybe certain molecules adsorb to the surface differently. And it's that's a very interesting question. But generally speaking, I'm gonna say the answer is no. There shouldn't be two electrochemically active surface areas, at least not to our understanding and knowledge. Let me see. I'm just looking at some of Chris's things. Well, actually, Chris said he was responding to Fred. If you're looking to optimize a coating, there is a lot more complexity involved at the nanoscale. Oh, yeah, and secondary chemical reactions. Yep, absolutely. I'm just talking about the macroscopic things that you can kind of do. And then you need to actively control growth at the surface, sometimes using brighteners to attack high stress areas. And yeah, maybe, yeah, electrochemistry on zeolites. Yeah, I haven't done electrochemistry on zeolites, so maybe that is a reason why I don't know enough about it. About maybe the possibility that there are two electrochemically active surface areas. Let's see. Fred's asking, is it possible to do Mott-Schottky on thin films that are not coated completely with the material? I can't get the right curve. Even after the following the literature 1-to-1. Oh, interesting. Okay, so I'm trying to think about if you don't have a completely coated thin film material. Okay, I'm going to say that if it's not completely coated, so most of these semiconductors are relatively, I'm gonna say relatively thick. But I do think that you're gonna have some problems with Mott-Schottky if it's not completely coated, because you expose all these other electrochemical processes that can dominate the Mott-Schottky response, and hence you're not gonna get proper signal. But Mott-Schottky it's tricky. Neil is learning a lot about Mott-Schottky, and let me just say, hold on. He's saying no. The substrate has FTO, fluorine tin oxide, on the whole surface. Okay. Oh yeah. Wait. Yeah. This is in response to Chris saying, "Can you mask off uncoated portions?" And Fred saying, "No. The substrate has FTO on the whole surface." Okay. Well, so you have the FTO, and then you're saying, but if a thin film, but it sounds like you have the FTO on the whole surface then. But maybe the area where you're doping doesn't have, maybe that's it. Maybe the area that you're doping, that area is exposed. Mott-Schottky is challenging. Just the technique itself. I mean, you push some buttons on an instrument, I guess. From that level of challenging, it's not that hard, but because you hook something up and then you push buttons, but getting the substrate right, cleaning it correctly, removing native oxide films. Let's see. I'm coating the substrate with FTO with another material, copper oxide. Okay. Oh, so I'm coating the substrate with FTO with another material, C2O2. So it sounds like you have two metal oxide interfaces, possibly, in this situation. Maybe. I can understand using FTO for a semiconductor photoelectrochemistry type of thing. If you want some transparent things. So yeah, okay, glass substrate, conductive material FTO, and then the material. And my material is C2O2. Let's see. So I think this is going to be. I think this is going to be fairly challenging to do because I don't know enough about. Actually, I've used FTO. I've used Indian tin oxide. Actually, no. I used ITO. I had Indian tin oxide one time, but fluorinated tin oxide. I think the reason why this is complicated is because you have an insulator. So I'm assuming these are things that you buy from like Sigma Aldrich or something like that. They have two like silver bus bars on it. So it's a glass, some Indium tin oxide, or some FTO, some bus bars to make electrical contact. But what you're really looking at, what's in solution, is you have glass, you have a semiconductor, and then you have another semiconductor. And then if you want to, you can even say like, all right, well, that's silver epoxy or something that the bus bar that you're clamping to, that's a conductor. So you have a conductor. Yeah, bought from Sigma. Yeah. I think I've used some of these things before. Let's see if I can find it actually. Sigma Aldrich. Actually, I should do millipore Sigma because that's technically what it is. FTO. Fluorine doped tin oxide coated glass slides. So I'm just doing a Google search right now. They don't have any pictures. Reasonable conductivity, 13 ohms per square centimeter or square. It's 50 millimeter by 50 millimeter, 2.2 millimeter surface resistivity. Yeah, it's transmittance. Yeah. So the I don't know if FTO chemistry comes in. Yeah, so I just think about having multiple boundary interfaces. Additionally, like it's fluorine doped, so I don't know if it's like a N doped or P doped or N type or P type semiconductor. I don't know if that's it. I also don't know, like some of these semiconductors to do good Mott-Schottky in solution, right? You need to remove a native oxide film that can form on these things. But yeah, having two semiconductors, one on top of another, that really complicates the chemistry a lot. So my very limited understanding of these things, just moving on here, is that you have. So first off, you got your like little silver. This is like your silver bus bar, right? And actually, maybe I do this a little bit differently. So you have a silver conductor. This is your silver conductive bus bar. You then have a film of ITO. And this ITO actually doesn't look like this from an energy perspective. It actually looks a little bit more like this. You have a conduction band and a valence band. And there's your band gap. And this is the ITO. And then you have a C2O2, or sorry, C2O. And that also has a conduction band and a valence band. And all of these are like, they're touching each other, right? Because you're depositing them. So like I've drawn these like kind of all together, sort of say, but all these have some kind of Schottky barrier. This is a Schottky barrier. There's a barrier here. There's a barrier there. the impedance of this thing is it just looks like it would be super complicated. And then I don't know the doping level, because the Fermi level of your silver, which is what you can control, there's the Fermi level here. It could be here if it's N doped, or here if it's P doped. It could be here. Well, this whole thing can be like up or down relative to the ITO. So I just think that I don't know enough. I just think I don't know enough about this system to really understand what's happening and why your Mott-Schottky is or isn't working. I just know it's just complicated. It's a very complicated, like, photophysics type of system. So I'm sorry, Fred. Keep asking us these questions, and one day we'll learn enough about them. Let me see. Superb has a question. In screen printed electrodes, how to make the silver reference electrode not get oxidized over time? So silver will naturally oxidize over time, just thermodynamically. If it's just left out in air, that'll happen. So what you can do to protect it is you can actually put you can take your screen printed electrodes, and you can put them in a small, either a vacuum chamber or in like a nitrogen glove box or something like that. Store them under nitrogen or vacuum seal them additionally. That is a great way for storing them so that they don't oxidize over time. But eventually they will oxidize when exposed to oxygen. So that's the only kind of problem with kind of the silver reference electrode. But it should be in the form of silver chloride. But if you plated silver on it, for example, and you want it to not oxidize, then I would stick it in something that does not have it's removed from oxygen. So there are many ways of vacuum sealing it. I mean, you can even buy something like you can get these kind of inexpensive, just like freezer lock containers that vacuum seal something. Not super expensive, but that's a way you can store your screen print electrodes. So hopefully that's helpful. Fred saying, so in summary, it's hard to do Mott-Schottky if the coating is not completely, not complete or thick enough, if I understand correctly. Yes, and I also believe that fundamentally, like, your system will also kind of govern how good the Mott-Schottky data is. Like, that might be one reason why your, because Mott-Schottky is it's a linear expression at the end of the day. 1 over the space charge capacitance squared is equal to, a bunch of stuff with the flat band potential as you change, the potential, or as a function of potential, and you should get a straight line. And if you don't get straight lines, then the system is not obeying the Mott-Schottky principle, or you don't have a good Schottky barrier. There's some other thing going on. So I think it's cool. I think it's a neat thing. I do not know enough about it. Fred's saying, Chris, I prefer not to add other ions into the bath. Yeah, it looks like he's doing some plating stuff. Yeah, no. I mean, I think these are all very good questions, good concerns, good comments. Let's see. Right now we don't have any questions, which is fine. We have good conversation. I'll wait around for a bit longer. Let me just check to make sure. There aren't anything on Twitter, for example. As a heads up, let me just see. Okay, so as a heads up, next week we will not have an Ask Us Anything about electrochemistry. I will be at Villanova University doing an electrochemistry workshop. So I've been doing a lot of electrochemistry workshops, and I'll be traveling a lot this summer. So both Neil and I are traveling quite a bit this summer. Neil's on vacation, but then he has other work conferences and stuff like that. So just kind of a heads up about next few weeks, rest of summer. We're going to try our best to do as many of these as we can when we have time. But but yeah, just a heads up about next week. And if you're interested in having us do a workshop in your neck of the woods, contact us. If you're in the U.S. and you're interested in having us actually teach some level of electrochemistry, let's at least start a conversation and figure out the logistics, because we're happy to do those types of things. All right. Gary has a question. Gargi, I think. Okay. Again, don't pronounce names very well. How to insert solid gel electrolyte within a micro supercapacitor interdigitated electrode. Can you please discuss about micro supercapacitor design for high performance? So Gary, I'm going to tell you right now, I have no clue because I've never had to work with or deal with these kinds of things before. An interdigitated array electrode is like having like kind of one set of electrodes and the whole like another set, and kind of moving them, kind of in between each other, very very low spacing. There's maybe no more than a micron or 10 microns between electrodes, and those are usually two working electrodes, and you have a little bit more control over, say, like diffusion and things like that. But I don't know. This is the first time I've heard the phrase micro supercapacitor, digitated electrode. But I would suspect if you have you said a solid gel electrolyte. I mean, to a degree, I might just press the electrolyte onto the interdigitated array. The interdigitated array is maybe like a screen printed electrode that sits on top of a thing. And you might just take a droplet or like a piece of it and just gently press on it. If it's a gel electrolyte, right? So it might be kind of funky or so, but I don't know what it looks like, but I would say maybe just like pressing something and applying a bit of pressure might be the way to go. I've worked with some gels, because some gels, you may even want it to sit for a while to kind of equilibrate once they're in solution. So that's just my thought, but I do not know enough about micro supercapacitor interdigitated electrodes. This is one of those questions that's a little bit too specific for me to know anything about. But thank you, Gargi, for the question. I'm sorry if I'm unable to really provide any additional support about these kinds of supercapacitors. This is the first time I've ever heard of one, but that design makes sense. I can understand why someone would do that, because if you have if you're using like the electrical double layer, for example, as your capacitor, and then you have multiple double layers kind of in a row, which is what the interdigitated array does, then you can kind of charge and discharge them on and off, and the sum of the capacitors adds to the capacitance. The rules for how, like, what's the capacitance if you have two capacitors in series is different than the rules when they're like in parallel with each other. And I forgot exactly what the equivalent capacitance is, but overall, there are ways of configuring lots of little capacitors to create big capacitors, and I think that's what these micro supercapacitor interdigitated electrodes are designed for. So you're welcome, Gargi. I'm sorry I can't be more elaborate on it. All right, so Zaki asks a question. We get Tafel constants at high overpotentials. For diffusion/mixed control, we don't observe Tafel region. Is there a way to find Tafel constant for diffusion/mixed control processes? So let me see if I can understand your question correctly. We get Tafel constants at high overpotentials. For diffusion mixed control, we don't observe Tafel region. Is there a way to find Tafel constant? Control region. Probably not. The doing things like Tafel analysis and getting Tafel constants when you're at high enough overpotential, like the math. I mean, to a certain degree, you could try to solve those equations with both contributing factors, right? So, I haven't done too much. I'm still working on my slides for like Tafel analysis and Tafel equation, but like you have these Tafel constants, right? And you have the Tafel equation. And because it's like base log 10, you need to be at a sufficiently high overpotential to really see, to use these values just because of how, let's see, so let's just go here. Not that I'm the best artist when it comes to describing Tafel stuff. But if I draw it this way, and I know that there are many ways of drawing it. So if this is overpotential, which I use eta, and this is log of the current, not drawing very well. Log of current looks like a lag, but it's log current. You end up seeing something like this. It like curves at the end and then it's straight. So there's a curving that occurs in this region where the overpotential between these two is this is the mixed region. And so these are straight lines. You can get slopes, but these areas inherently are not sloped because they have contributing factors. This mixed region. It's not even really well, I mean, there is some level of diffusion control, but like these mixed regions have these contributing factors from both sides of the Butler-Volmer equation, right? So it's easy to solve this expression when one half is out of it, but it's much harder to solve both of them to get like a constant or to get like a slope, sort of say. So I would even make the argument that you really like, and I've spoken to other people about it, and it's actually, frankly, it's mentioned in Bard and Faulkner in Electrochemical Methods, Fundamentals and Applications. You really can't use the Tafel constants or even Tafel analysis if you have very fast kinetics and you're in this like mixed diffusion region. Just because it's a mixed diffusion region, you have contributing factors in the current associated with other things. So unless you looked at the full expression, then you wouldn't have, there isn't really a slope here. It's no longer linear in this mixed diffusion region. So I hope that, I think that was what you were asking, Zaki. I hope that helps. I don't know for sure, but generally speaking, like you wouldn't say, oh, I have, this is the Tafel constant in the mixed region. I have the anodic region, the cathodic region, and the mixed region. Well, in the mixed region, that's when Tafel analysis breaks apart and doesn't work very well, especially if your system is has fast electron transfer kinetics and there's not sufficient overpotential between the two halves. Okay, all right, let's see. Moving on. Okay, Fred is asking, any tips for equivalent circuit fitting? How big of an error is still considered good fitting? I've been changing values for hours to get a good fit. Let's see. I hope the Warburg region in the low frequency can be ignored. That's the hard part to fit. Okay. Well, if you know it's a Warburg, oh yeah. Okay. So you're hoping that it's Warburg. So tips. So, I will say that Neil has an entire EIS webinar series, Fred, which I think, if you're a tier 2 YouTube member, we have webinars on EIS, and some of the last, actually, I think even the last 2 webinars that Neil did on EIS has to do with tips and tricks associated with circuit fitting. just things that you can do, and just, I guess, briefly, because I don't do that much circuit fitting, but let me share my screen with Aftermath. All right, so if I don't know if I have any. Let's see. So if I have some random EIS data, okay, so I have some random EIS data that is not very good. But if I were to try to do a circuit fit, so let's just do circuit fit. So you need to pick the right circuit. I don't know what the right circuit is for me. I'm just gonna pick this guy, but you're not seeing what I'm showing right now. But okay, so this one's not correct clearly, but a couple things that Neil goes over in his webinar is picking the circuit that fits picking the circuit that's represented a physical reality. So that's one very important thing to do. Adjusting a parameter like one at a time, and then locking the other ones while hitting the calculate button, for example. So that iterate, it's much easier to optimize one parameter at a time if you lock the other ones. And then when you're done, it's just like, okay, well, I want to do this one now, and I want to optimize for this. And then I hit calculate and stuff. So that's one thing that you can do. This is Neil's least favorite thing, but he hates chi-squared. Look at your error statistic. If you have a very, very low chi-squared value, and what is low, that's another thing to help support your, how good a fit your EIS data is. But one thing for you, Fred, specifically, is there is this weighting feature that we have in Aftermath where, you could remove data points, right? So I can say, that's a bad one. That's an outlier. And it just gets removed, and you can see it here. It's just gray. So if you wanted to do some fitting where you've removed that data point, and maybe you don't want to remove it completely, maybe you still want part of it, so maybe you just weight it mathematically by half, for example. So this data point is only mathematically treated, as half of its weight when calculating the fit. So that's just kind of the simple type of thing. I'd look at the Bode plot. I'd also look at the Nyquist plot, because things that look good in the Nyquist plot might not look good in the Bode plot. Things that look good in the Bode plot might not look good in the Nyquist plot. You really want things to be good with both of them. And sometimes you really have to zoom in to see how well does a certain fit show. Neil has examples of these. He goes into it in more detail in his webinar, but yeah, those are kind of those are my very, very quick tips for equivalent fitting, equivalent circuit fitting. So I'd watch Neil's webinar for more, but that's the gist of it. Okay. All right. Looks like we don't have any more questions so far. We will still try to answer as many questions. I will be out of town next week, again, doing an electrochemistry workshop at Villanova. And then 2 weeks after that, I'm doing another electrochemistry workshop. So I am getting saturated with electrochemistry workshops, which is a good thing. I like doing them. I like seeing you guys in person, either at ECS meetings or at workshops or anything like that. So, of course, if you have questions, leave them in the comment section of our YouTube channel, and or just you can email us as well. But the YouTube channel, we respond pretty quickly, relatively quickly. All right. Okay, so that is. I think that I've said all of the things. There doesn't seem to be any new upcoming questions. I might wait just a little bit longer. But just have a sip of water first. there are some upcoming. Just let me see if there's any upcoming trade shows. There is the American Chemical Society meeting in August that I will be attending. So if you want to see us there, my colleague Tim, who you haven't met, he will be at the BCCE. That's a bicentennial conference for electrochemistry, or not chemistry, chemical education. There will be an ISE, International Society of Electrochemistry meeting in Montreal. So if you're there, you should go say hi to Neil. That's most of these are in August, so that's like August 18th to like the 23rd. Maybe it's not that long. Actually, no, it is that long. They have very long meetings. There is, let's see, there's Cermax. There is, if you're in Europe, there is, I believe, an ISE topical meeting in Manchester. There's GDCH Electrochemistry in Germany. I'm not even going to try to pronounce where that's located, but yeah, I think you get the idea. Okay. All right. Well, I think that's about it. Thank you again for tuning in to another episode of Ask Us Anything About Electrochemistry. I'm Alex, and I'll see you soon.